While they're coming on in, I'll introduce them here. This is John Patterson, Dave Gallant. We've got two more coming. Of course, they're always slow out there. They're drinking their coffee, catching up. Sebastian Sobolewski. We got Paul Ashmore. So this is the core architects for the product, for our technology, our software stacks, all the way up and down from UI, user interfaces, some other stuff we'll talk about here, data path, as we get through some of these presentations. Feel free to ask questions. You guys know me from last year, a lot of you do. I'm very open. Ask, we'll bounce around. These guys are very open. They can answer almost any question if I can't answer it. Last year I did what I could, and you can get the details on everything from these guys. So. Yeah. No, I don't. I wish I did. I'll probably stand over this way so you guys can all see the slides and you can see the crew here. So some of our technology challenges, as we're trying to go down through all this, you've heard us talk about the performances, PCIe flash, how to operate there, what we need to do. That's one of the best ways to use it. We got the speeds and the feeds and the capacity. So a balanced hybrid system like this is quite difficult to do. Active-active, as Chris already mentioned. We've got some crew here that've done active-active systems in the past, and some of our challenges with that. We made an intentional decision for the market to go after that. It was a little bit of effort for us, but we knew that up front, and we knew we'd go bite off that bullet and keep coherency between an active-active system. So we can talk about details on that and how that all plays out throughout this system here. But some of our goals, keeping that dollar per gig kind of low. For that functionality in our market, you really need to use solid state where it's good, hard drives where they're good, kind of hit that dollar per point, as you see that David and John had talked about earlier. You know, we're not a pure solid state system, which gives us a lot of good economies of scale that put us right in that mid-market, which is a very large market for us. There's always value for folks above in the solid state and folks below in just pure disk, as we just hit on earlier too. So.
Hey Kelly, why don't you talk about the software architecture and how each IOB comes down
Sure.
and you're deciding about where it lands?
Okay. So actually, I might actually toss some of this one off to Paul. Our architecture, I'll hit it quickly and I'll let him chat about it. So our stack is built very modular all the way up and down. We use a C++ object-oriented interface all the way up and down the stack. We have functionality that we can implement in smaller modules and test them. And IOBs, an IO will come in at the top of the stack. We convert it IOB, our generic term. It's basically a SCSI CDB with our additional functionality and features. And I'll let Paul talk a little bit about the stack and how that runs and how the interfaces there are. Talk about our stack and how we laid that all system out and how it's dynamic and what we can do with it.
So, as Kelly just said, we took an object-oriented approach to the stack. And what that really means is every one of the functional modules in there know how to handle commands coming in and going out, and they all have a common interface, which means that when we need to create new capabilities, all we have to do is change the algorithm inside those modules, and we don't have to worry about handling IOs. It makes it very quick for us to develop new features. And I think Chris just mentioned that how an IOB lands in different places. We have several modules to handle I/O, some that deal with QoS, some that deal with deduping, and then there is the tiering sections. And if you want more detail, I can give it.
I'm interested, did you call it I/O control, where you kind of apply business policies to see where it goes to SSD or HDD? Is that truly a business policy, or is it more like, I use this data more, so I'm going to put that on SSD? And
So it's based on our QoS engine. So every IO has a policy it's in, it has a level it's in. We'll tag it. It's part of the additional functionality we add on an IOB. And then up and down the stack, we can inquire on how we need to handle that at any one of the different modules. So it's all the way up and down throughout the stack, and our QoS is kind of tied in from that. I don't know if we've got some slides or if you guys have seen presentations of our UI or any of that. These guys have some of the details on that too. But
and is the QoS, like, do you guys set that up, or does the customer kind of contribute to that?
We're capable of doing a lot of variety on that. We currently set up 5 policies that we've exposed. Hitting a market with kind of a new functionality, new feature, new usability, that's resonated really well. And Chris is probably better at answering that. But In the code, we can actually be very flexible and give them really fine-grained knobs on things. But we give them the 5 policies. Here's quick and easy. Here's how they play with each other and set them all up. And I don't know if maybe Seb can talk a little bit more about some of the details on how some of those get hit and policies and up and down if you want. But it's every IOB. Every IOB is tagged and can be adjusted up and down the stack.
And the whole notion was that a customer, when you have a system like ours where there's huge amounts of capacity on it, they're not going to use it for one thing. They're going to use it for a variety of stuff. And the policies allow customers to say, okay, this is my really important data. I want this stuff to go fast no matter what happens. So we give them those policies, and they can put that in their mission critical policy, which means that IO is going to get serviced and get serviced very quickly. And then you can have your, I don't know, your little garbage bin or shared folder that you're sharing with a bunch of people. That's not as important for performance, but you want it to perform well, but not at the cost of your, say, exchange environment. So you can put that in a lower policy, and we're still going to service that IO, but when the system is swamped, we're going to prefer to service the exchange and slow down. Basically, that's going to have the net effect of slowing down the less important data that you want. That's basically what the IO control gives you. It gives you the flexibility of being able to use your SAN to its fullest power when it's available, but not to take a hit on your really important apps.
If the swamp takes place during or with a couple of VMs or applications that are all in a high profile.
And they're all going to share that profile's IO workload. So if you have 5 applications, they're going to split 5 ways. But that's so if you have an Exchange cluster and you really want all those 5 guys running, they're going to run at the same rate. If you have one of those VMs and it's not as important to you, you can shift it down to policy level, and the other 4 will get the performance increase because you've taken the 5th one down to policy notch. The system has enough IOPS to be able to handle quite a heavy load. I'm not sure if Chris is going to talk about that later or not.
I think we flashed a quick slide up, but I don't think we got much detail. We'll just ask the questions more. Does that kind of answer what you were looking at there? Yeah.
Can you do a quick run through the data reduction?
Data reduction side of things, okay? Sure. I'll probably toss this one off to Paul again, too. So it's actually a multi-phase data reduction. We still have some phases to build out on it, but right now we have we call our simple dedupe, or our first pass, first phase dedupe up top. Again, it's one of the filter stack modules, so we can kind of adjust it, move it up and down, replace it if we need to, if we find something better or more effective, so we can replace it. But I'll let Paul talk about it in its details.
Yeah, we maybe I should tell you the name. We call it simple dedupe, and it's primarily designed as a performance booster for virtual machines and VMware. We recognize the data patterns that they use most frequently, and then we accelerate them. We do save space using that as well, but really it's a performance enhancer. And that's quite high in our I/O servicing to give good response time. And then in the back end, as well as saving space when data becomes unused, we also go and look for other special patterns and matching data patterns, which allows us to clone volumes, and then all we need to do is record how many times a particular data pattern is used, and not actually record it multiple times.
And so that's also integrated into the snapshot mechanism?
Yeah, the whole of the stack was designed from scratch, and it's not based on a legacy architecture. So inside the core I/O path, we built snapshots and several flavors of dedupe and QoS and thin provisioning and some other things that maybe will be released as a product one day.
You're such a tease.
Yeah.
But until the patents are allowed, I can't tell you.
Yeah. So, I guess we already kind of jumped into the I/O stack here, so I'll kick through some slides here. You guys know from the past, I kind of like to do a very informal. We'll run through the slide deck's kind of a reference for me. You guys also have it, so feel free to ask questions as you go anywhere on that. So, So Paul's already mentioned that we can talk a little bit about PAWS. It's probably not what you think. We actually call it Paul's operating system. Paul actually kind of laid out and designed all of the Linux stack and the Linux core and how we actually build up our Linux infrastructure. It's very tuned and optimized for us, very specialized. So it's not a off-the-shelf like Red Hat, Slackware, any of those. It's very tuned and customized for us. We actually build it with our own system from source, from the open source community. So I don't know if you want to chat about PAWS a little bit and its functionality and features.
Yeah, POS was designed really so we have control over the entire universe, and if we discover a problem in some open source software, we have ownership of fixing that problem and not relying on the open source community to do it, because that could take several years. We just get on and fix it. So we build the entire operating system. We don't take packages from anywhere else, and that goes from all the way down to the tool chain, to our distribution, to all of the command line tools that we have inside. And another thing that I'll say about the way we build our system is it's designed to be read-only. So most Linux-based systems will use an initial RAM disk and then switch over to a read-write disk. And lots of embedded systems in the industry, they do that, but we don't do that. We just stick with everything out of RAM in our RAM disk. And the reason I wanted to bring that up is because it gives us much more reliability when we're reading and writing flash, because we're not constantly changing flash, which wears the flash chips out. We just boot and run from RAM.
And Paul hit on some key points for us. You know, we debated whether or not we wanted to go down with a stock Linux kernel or a Linux distribution to get off the wire, and we chose not to for a lot of the reasons he's mentioned. It's very customized, it's very optimized for us. We don't have a persisted storage that we're relying on for that. Read it up out of a persisted storage, we run from memory at that point.
You are using the real-time features of Linux or not?
So it's one of the other advantages I was going to describe quickly here, is that as we find problems and changes, we can adjust and change and move forward quickly. I'm not waiting for Red Hat to say, oh great, here's your new release, right? So the real-time side of things, from different options inside the kernel, it's truly optimized highly for us. And there's no background processes are running that we haven't approved and had validation and need functionality. Real-time, as far as the real-time kernel patches, real-time turned on, we don't quite run in that mode. We could, we just haven't needed to yet.
We do change the scheduling policy of the way threads are scheduled. And I think we really need to, because the hardware that we run on has 12 hyper-threading cores and a lot of memory, a lot of RAM.
No, this is the same strategy used by other SSD vendors.
A lot of them, yeah. Ours is really highly optimized for our environment, as Paul mentioned. I mean, it's tuned and tweaked in every possible way for what we do. All kinds of stuff is just flat out turned off, not compiled in, not giving us any trouble. So as far as the true real-time kernel settings, we haven't turned those on because we haven't needed to yet. We can turn them on if we need them, though. That's one of the great things about compiling it ourselves.
Making it easier so also for them with the problem.
Yeah. And back to kind of on the board, we had talked about it. You know, we are a kind of one throat to choke, if you will. If there's a problem in the kernel, we stand behind it. We go fix it. We get it done, right? We've actually pushed some kernel changes up to kernel.org that are problems in the kernel, and we usually track them down to root cause and hand them off to the crew that's responsible for upstreaming them. But we found a few problems in the kernel and pushed them upstream already. So, yeah. So it really reduces our time to market, gives us all that flexibility and functionality for bringing new hardware, new platforms online as we need, and gives us what we need to be effective at it.